Welcome to The Explainer. Today we're diving into a force that's, well, it's pretty much everywhere. It holds the atoms together that make you, you, and it's also responsible for that annoying static cling on your clothes. We are talking about electric charge, and you're about to see how it literally shapes everything around us.
Oh yeah, you know this scene. You pull your laundry out of the dryer and a sock is glued to your shirt. It seems like such a small thing, right? A minor inconvenience. But it's actually a perfect everyday glimpse into one of the fundamental forces of the entire universe, electromagnetism. And the whole story starts with charge.
So, here's our game plan for this explainer. We're going to start with a quick trip back in time to see how we even figured this stuff out. Then, we'll get right into what charge is, how it moves around, and finally, we'll unpack the three absolute fundamental laws that govern its every move.
Okay, first stop, the world of electromagnetism. And you know, this isn't some new discovery. This is a story that has unfolded over thousands of years, starting with just a strange observation and ending up as one of the most successful theories in all of physics. It all kicks off with the ancient Greeks. They noticed that if you rubbed a piece of amber, it can magically pick up little bits of straw. For centuries, that was just a curiosity. People thought electricity and magnetism were totally separate things. Then, bam, 1820. Hans Christian Ørsted is giving a lecture and he sees an electric current move a compass needle. The two are connected. After that, you get the absolute genius Michael Faraday, an experimental wizard who could see the forces in his mind, but famously didn't write a single equation. And finally, James Clerk Maxwell comes along, takes all of Faraday's brilliant ideas and translates them into the language of mathematics, giving us the complete theory of electromagnetism we use today.
So all that history brings us right to the heart of the matter. What in the world is electric charge?
Okay, so here's the key thing to remember. Charge isn't something you add on to a particle, like paint. It's an intrinsic property, just like mass is. It's part of what a particle is, and it only comes in two flavors, positive and negative. That's it. Most stuff we see every day is electrically neutral, meaning it's got a perfect balance of both. But when you mess up that balance, say by rubbing a balloon on your hair, well, then we say an object is charged. So how do these charged objects talk to each other? It all comes down to one simple golden rule that explains everything else we're about to cover. Charges that are the same, they push each other away, they repel. And charges that are opposite, they pull together, they attract. It's that simple. Likes repel, opposites attract. And this is that rule in action, plain as day. On the left, you've got two glass rods. They've both been charged up to be positive, and you can see they're pushing each other apart. They repel. Then, on the right, you have that positive glass rod and a negatively charged plastic rod. And what do? They pull right toward each other. They attract. This simple push and pull is the engine behind all electrostatic force.
Okay, so we know charges can push and pull, but the next logical question is, can they move? And the answer is, it totally depends on what kind of material they're in. This brings us to a really crucial difference between two types of materials, conductors and insulators.
Think of it like this. In conductors, like copper wire, some of the electrons aren't really tied to any one atom. They're called conduction electrons, and they're free to just roam around the material like cars on a freeway. But in insulators, like rubber or glass, the electrons are locked down tight. They can't go anywhere. And then you have this interesting middle ground, semiconductors like silicon, which are the absolute bedrock of all our modern electronics. Now this is where it gets really cool. Look what happens when you bring a charged object near a conductor. Here we have a negative rod, and we're bringing it close to a copper rod that's totally neutral. All those free-roaming electrons in the copper hate that negative rod, so they get repelled and skedaddle to the far side. What does that leave behind on the side near the rod? A bunch of positive atomic nuclei. So now, even though the copper rod is still neutral overall, one side of it is positive and one side is negative. And that near positive side is now attracted to the rod. This is called an induced charge. So we know charges attract or repel. But by how much? How strong is that push or pull? To answer that, we have to go from just describing it to actually measuring it. It's time to put a number on the force. And we do that with something called Coulomb's law. This law is named after Charles Augustin de Coulomb, who worked all this out way back in 1785. It is the absolute bedrock of electrostatics. It gives us the power to calculate the exact strength of the force between two little charged particles. And there it is. Now, I know equations can look a little intimidating, but let's break this one down. It's actually really simple. F is the force we want.
On the other side, K is just a number, a constant. Q1 and Q2 are just the amounts of charge on our two particles. You multiply those together. Then, and this is the important part, you divide the whole thing by r squared, where r is the distance between them. The big idea is simple. The more charge you have, the more force you get. But the more distance between them, the way less force you get.
Now let's focus on that inverse square thing, because it's a huge deal. That's the part where you divide by the distance squared. It means that the force gets weaker with distance, fast. I mean, really fast. If you double the distance between two charges, the force doesn't just get cut in half. No, it drops to 1/4 of what it was. It plummets.
Okay, but what if you have a whole bunch of charges all interacting? Well, it's surprisingly simple. The forces just add up. The only catch is that force isn't just a number. It has a direction. It's what physicists call a vector, so you have to add them up like arrows. As you can see here, you figure out the force from each individual charge on particle 1, and then you just add those force arrows together, tip to tail, to find the final net force. This powerful idea is called the principle of superposition.
All right, our next big idea is a bit of a mind bender. It's one of those weird facts about the universe that's just so cool. It turns out that electric charge isn't some smooth, continuous fluid like water. It actually comes in tiny, individual, indivisible packets.
This property has a name. It's called being quantized. It means charge only exists in specific, set amounts. Think of it like money. You can have $1 or $2 or $10, but you can't have a single coin worth $1.50. It just doesn't exist. Charge is the same way.
Any amount of charge you will ever measure, which we're calling Q, is always a whole number multiple, that's the n, of this one fundamental unit of charge, which we call E. So you can find something with the charge of, say, plus 10e or minus 6e, but you will never, ever find a particle with a charge of like 3.57e. The universe just doesn't make charge that way.
So just how small is this fundamental packet of charge? It's about 1.6 times 10 to the negative 19 coulombs. I mean, that is a decimal point followed by 18 zeros and then a 16. It's an unbelievably, unimaginably tiny amount. A single proton has a charge of positive E, and a single electron has a charge of negative E.
And here's where you can really see just how ridiculously powerful this electrostatic force is. Look at two protons sitting next to each other in the nucleus of an atom. The electrostatic force trying to push them apart is about 14 newtons. Now look at the force of gravity trying to pull them together. It's 10 to the negative 35 newtons. That number is basically zero. This huge imbalance tells us something profound. There must be another, even stronger force in there, the strong nuclear force that's winning the fight and holding that nucleus together.
And this brings us to our final fundamental rule of charge. Just like energy, just like momentum, electric charge is conserved. In any isolated system, you can move it all around, but the total net amount of charge can never change. You can't just create it out of nothing or make it disappear.
This picture is incredible. It's a photograph from a bubble chamber, and it's basically a perfect visual confirmation of this law. What you're seeing is a gamma ray, which has zero charge, so it leaves no track, coming in from the bottom. Then right at the point of that V, it spontaneously transforms into two new particles. It creates an electron with a charge of negative E, and its antimatter twin, a positron, with a charge of positive E. So what was the net charge before? Zero. And what's the net charge after? Negative E plus positive E is still zero. Charge is perfectly conserved. It's beautiful.
So let's end with this really fascinating puzzle. We've seen that the electrostatic force is outrageously, monstrously stronger than gravity, like 10 to the 36 times stronger. So why is gravity the one in charge of building planets and stars and entire galaxies? Why doesn't the electric force run the universe? And the answer is actually really elegant. It's because charge comes in two types, positive and negative, which can cancel each other out. Any large buildup of positive charge is going to attract negative charges and repel other positive ones, so things stay pretty balanced on a large scale. But gravity only does one thing. It only ever pulls. It's always attractive. So over cosmic scales, it can just keep pulling and pulling and pulling, building up the huge structures we see all across the cosmos.